Okay, the recording has been started. Thank you very much for attending this last lecture. To summarize, we have an appointment in the lab, which is walking distance here, 5 minutes, at 11, and we will stay there about half an hour, 35 minutes. Before 11, we will make the break, about 20 minutes. If you want to follow me for a coffee, as I anticipated, you are welcome. And I'm very pleased to invite you. And it will be between 10:40 and 11, more or less. So now we have about 1 hour and 25 minutes of lecturing. I am moving forward with the conclusion of our discussion and the treatment of decision making. I wanted to go back to our page to summarize. To summarize where we are. We are at the last lecture, of course, and these are the links that we dealt with. I will make a recap at the end of the lecture. Okay, so I will take about 10 minutes to remind you what are the links that you have to prepare for your exam. Okay, and exercises. Actually, I had in mind also, and it's available here, and our last exercise on what we do today. And of course, we will not have time to make it. You don't have to worry because the exercise, as you know, it's not a subject for the exam. On the other hand, you know what is the purpose of exercises is to practice yourself and they help you to better understand the theory, which is part of the exam. And therefore, my suggestion, if you have time to have a look at this exercise before the exam, it may be useful for your preparation. Of course, you don't have to do that. It's just a suggestion. I think you are able already to have a look by yourself. There is an R code, and therefore, I think, let me see. There is the suggested R code here inside the file that you download when you click over the link of the exercise. So you have already the experience and the skills to understand the R code. And as I said, it may be useful for you to practice and therefore better remember. So what are we discussing today? You remember what we already discussed, which is related to decision theory. And in particular, we discussed several methods for taking robust decisions. All of these methods share at a certain point an assessment of the performances of different alternatives, different possible alternatives. And then I told you that the assessment needs to be based on some performance requirements, some modeling, some way, some structured way of understanding, basing, for instance, on an objective function or several objective functions, as we said. The assessment allows us to understand what are the benefits that each alternative may offer, and therefore to select at the end of the story the best one, starting from a bottom-up approach rather than a top-down. But at a certain point, you have to make this assessment. And how to make this assessment is the subject of our last lecture today. And as I anticipated to you, I take to the right place, we will discuss one possible solution, which is called analytical hierarchy process, analytic hierarchy process. It's a structured techniques for handling complex decisions, and in particular, as you will see, to estimate in a comparative way the benefit that each alternative may offer. Here you see that there is a link. Indeed, this is a well-known method. The link brings you to a Wikipedia page, which is basically the subject of my lecture today. I will make a different example. This is an example related to job recruitment. And of course, the example is discipline specific. We will make a different one, but the procedure is precisely the same. This Wikipedia page is really well done. And I think that it may be a useful reference for you. But let's follow what is reported in my web page. And in particular, let me just put on the screen this, and 1 second, because the screen is shared, but I want to change the camera so that everybody can see over the screen that we have into the room. 1 second. Okay, here we are. So you can see what we are referring to. So the example that we are discussing today is, as you see in the title, related to decision-making in water resources management. As usual, when I have to find a practical example, usually I refer to water resources management because of my expertise. And in particular, we have to choose a solution for increasing water resources availability. We know that increasing the availability of water resources is one possible solution to cope with climate change, and in particular to cope with droughts, water scarcity in general. By the way, the difference between water scarcity and drought is that drought is a temporary water shortage, while water scarcity is a permanent water shortage. But both of them can be exacerbated by the presence of climate change, in particular because with the global warming, at least for the global warming, in conditions of water shortage, there is typically an increased evaporation and therefore an increased water demand, in particular for agriculture. We already discussed that agriculture is the main determinant of water demands. So what are the alternatives that are usually available for increasing water resources availability? The alternatives are typically increasing storage. Traditionally, increasing the storage is done through the construction of artificial reservoirs. They can be of different size. There is a rediscovery nowadays of the benefits offered by the solution of multiple small reservoirs instead of big ones, for obvious reasons, because of course a big one means big impact. Small reservoirs means a distributed impact which in general is less intensive in terms of environmental impact and in terms of several other socioeconomic impacts. The impact is less intensive with respect to building a huge reservoir. Moreover, small reservoirs usually accumulate water in a position that is very close to its final use, for instance, for irrigation, and therefore there is reduced water losses for infiltration into the canals, leakage from pipes, and also being the extension of these reservoirs reduced, also the losses for evaporation are reduced. And moreover, they can be easily covered by sun mirrors for producing clean energy, which is then used to vehiculate, to bring the water from the small reservoirs to the field, etc. So there is an increasing and renewed interest with respect to this solution that was practiced already a long time ago, because of course it requires less resources and was possible to apply this type of solution also in the past. Here you see a picture of the Vaillant Dam to summarize this alternative. And let's anyway not go into the details. It's a solution of increasing water storage, which may be sized depending on the local context, demand, etc. Another possibility to increase water resources availability is to reduce losses. And reducing losses can be done in different ways. For instance, by transforming the water transport from canals to piped solutions. Usually we use canals for irrigation because they require less energy, several reasons. They are cheaper, but of course, they present the problem of water losses for infiltration. A third solution may be, actually, it's not a solution to increase water resources availability, but it's a solution to reduce the demand. The third solution is to use what we call here precise irrigation, which means advanced irrigation technologies, which allow really to save a lot of water. Keep in mind that the losses in bringing water to the field for irrigation are about 50%. This is an indication that is valid worldwide. It's not a particular weakness of Italy. The statistics is for Italy. It's about 50%, and these losses are due to infiltration, evaporation, etc. And but as I said, it's an indication for Italy, but it's also an indication that has a general validity. And keep in mind that when we talk about piped water supply, the efficiency for Italy is about 65%, which means 35% of water losses. Italy is not very good in this. In other countries that are more complicated of Italy from the point of view of the morphology and therefore have less problems, they have efficiency that can vary between 70–80% in the north of Europe. So what I mean to say is that even if you bring water through pipes, you can't avoid losses because you have ruptures and they are not easy to be located. You see that there are losses, but when you have a network to manage that is about thousands of kilometers long, you understand that locating the position of a water loss, it's really complicated. So reducing losses brings, in general, a saving of which is very substantial. You may pass from 50% of leakage to something like 25%, which means a lot if you consider the volume that is available for irrigation. Precise irrigation, more or less, is the same. You can save, you can reduce the water demand by about 50% with respect to traditional procedures. Of course, it requires an investment because precise irrigation is not easy. While traditional procedures, like flood irrigation, for instance, simply are put into practice by releasing water over the ground, with precise irrigation, you have to bring the water precisely in correspondence of the stem of the plant, and you have to give the correct amount of water. So you have to get measuring devices that are very precise, digitally monitored. So, I mean, it requires a lot of investment. But these three solutions are frequently discussed. And you can call the solution 2 and 3 a nature-based solution because it's reducing leakages. It's not really implying a structural intervention. And it is something that optimizes the functioning of the ecosystem. And so you can call them nature-based solutions. Of course, if you increase instead the storage, it's not a nature-based solution. It's a structural intervention. Okay, so you see that, look at the sketch that you see with the block diagram, bottom left, three colors. You see the goal on the top. It's increase water resources. This is the goal, but we start from the bottom, from the analysis of the alternatives. You may remember, robust decision-making is precisely starting from the analysis of the alternatives. And here you see the three alternatives: dam, reducing losses, precise irrigation. And then we have to set out the criteria to evaluate the convenience of each alternative. I mentioned to you that usually we have the convenience to adopt several criteria. And here, in this example, we adopt 4 criteria. The first one is the net benefit. And let's call it with the symbol N, okay? In the following, net benefit will be identified by capital N. A second benefit may be the environmental impact measured in some way, okay? We don't go into the details here, but we can measure the environmental impact. When we make an environmental impact assessment, it can be measured in economic terms. It can be measured with indicators of environmental impact, like, for instance, the amount of biodiversity. This is one possible indicator. Or another possible indicator is the coverage by vegetated areas. Of course, you make a structural intervention, you reduce you change the land use, you reduce the amount of vegetated coverage, and this may be another indicator which is used, for instance, in urban areas in order to measure the environmental impact. So this is our second criteria, which we indicate with capital E. The third criteria is the impact on the flow regime. What does it mean? It means that when you build a reservoir, when you take water from a river, even without the reservoir, you generate an impact on the river flow regime. There is a deprivation of water resources in the river. So in some cases, this may be negligible, especially if you take a reduced amount of water, and depending also on the local condition, because if you have, it depends on the fauna, it depends on the characteristic of the ecosystem. But in some of the cases, especially when you get close to dry conditions, then the impact on the flow regime may become important, okay? And we measure it in some way. We indicate it with the symbol capital R, and the impact on the flow regime can be measured, again, by using indicators. We don't go into the details. And then another criteria may be the CO2 emissions that are implied by each solution. Of course, whatever we do, we generate CO2 emissions. We know that. And, but of course, different alternatives are characterized by different levels of CO2 emissions. And you know that the amount of CO2 emissions is today considered an indicator of human impact, let's say. One thing, when you select criteria, it would be important that these criteria are independent, because if they are dependent, you introduce a bias in the assessment. And let me make an example by referring to these four criteria. CO2 emissions may be also intended as an indicator of environmental impact, okay? They are, in a way, correlated to the environmental impact. Of course, it depends on how you measure the environmental impact. But in any case, if you put two criteria that are related to environmental impact, it's unavoidable that you put more weight on the broad sphere of the environmental impact. And, you know, this is a way to possibly introduce bias. You may say, okay, but I like minimizing the environmental impact, but think of the opposite. If one introduced four criteria that are all related to net benefit, it's clear that you put a lot of weight on the economic benefit, and this is at the expense of other criteria. So it would be better when we go into a discussion that we try to identify what are the main issues. So one main issue is the economic benefit, because the economic benefit is related to the socioeconomic functioning of the activity. So it is not just a matter of making money. It's a matter of providing a socioeconomic service. So it is important, fine. The environmental impact, it is important. And one should wonder whether the river flow regime CO2 emissions may be related to the environmental impact or not. And in this case, if you measure the impact on the flow regime in terms of touristic activities, commercial activities, may be not strictly related to the environmental impact. So, moral of the story, when you decide the criteria and how these are measured, try to generate criteria that are independent. Otherwise, if they are strictly dependent, you may just aggregate two criteria into one by maybe refining the performance measure, the way you compute it. So try to make this independent. In this case, it depends on how they are measured. how I measure the environmental impact, how I measure the impact on river flow regime. I just wanted to bring your attention on the fact that it's quite important. And therefore, you see that there are arrows, lines connecting each activity, each alternative, sorry, to each of the criteria. So this network of lines, they are just the connection between each alternative for which, for each one of the alternatives, we have to compute the 4 criteria, and therefore there must be a connection. And these lines are just the connection between, again, each alternative and each criteria. And you see that some of the lines are characterized by a rectangle where you see W1, N1. What is N1? This is easy. N1 is the net benefit related to alternative 1. Alternative 1 is the dam. So N1, once again, is net benefit related to alternative 1. And 1 second, because, yeah, okay. And then you have another line with W2 E1. Let's forget about W for now. What is E1? Is the environmental impact of alternative 1. Okay. And then we get to W4. Let's forget about it. And C1. What is C1? Is the CO2 emission of the dam. Okay. Now, what are the W? The W are the weight that we need to assign to each criteria. So what is the importance that we want to give to the net benefit with respect to the environmental impact or the impact on flow regime or CO2 emission? When you have more than one criteria in this method, you have to assign a weight to each of them. And you understand that this is a key of the procedure, because if you give weight 0 to the net benefit, it means that you don't care at all about the net benefit. If you give W4, CO2 emissions, W4 equal to 0, it means that you don't care at all about the CO2 emissions. So you understand that this is, I mean, something, it's a key of the procedure. And then we will see that indeed, the key of this method is the computation of the weights, which must be unbiased, transparent, whatever, okay? And the weight of each criteria is multiplied by the value of the criteria related to each alternative. So what is W1 and 1 is the weight of the net benefit, W1, multiplied by the net benefit of alternative 1, which is the dam. And in this way, by multiplying the net benefit by each weight, I get an indication, W1 and 1 is an indication of the overall convenience that I get from the dam according to the criteria net benefit. Okay. You understand that once that you have the value of W1 and 1, you can sum also the value W2, weight of the environmental impact, times multiplied by E1, and you can sum W3, impact on river flow regime, times R1, which is the impact of the dam, and you can sum also W4C1. By taking this sum, you get the overall benefit of the dam. So let me just change the camera and write on the blackboard. Good. So let's look at the figure. If I take the sum W1 and 1 plus W2 E1 plus W3 R1 plus W4 C1. What do I get? I get the overall performance assessment for the dam performance assessment for the dam. Because it's criteria, a weight of criteria 1 plus the benefit related to the dam for criteria 1. In this case, the net benefit plus weight of criteria 2 times the benefit. In this case, it's, I don't remember what is environmental impact of the dam. W3, weight of criteria 3 times river flow regime, perturbation of the river flow regime given by the dam, plus W4, weight of criteria CO2 emission times CO2 emissions of the dam, alternative dam. We can make the same computation. This is 1 for alternative 2 and alternative 3. And then at the end of the story, we see what is the most convenient solution with respect to the 4 criteria. Okay. Good. Is it the overall framework? Let me see if the camera is taking everything there. Not really. So 1 second. Now it's taking everything. Okay. And let me pin it. Okay. Any question related to the overall concept? Okay, good. Now, I already emphasized that one key here is the computation of the weights. So what is the weight that we should give to the net benefit with respect to the CO2 emissions, for instance? There is another key aspect here, another key issue, which I didn't mention. And the second key issue is that these criteria are evaluated with different units. So the net benefit typically is an economic, it's expressed in economic units. CO2 emissions usually are expressed in terms of kilograms or weights, okay, mass. Perfect. And so you understand that these units may lead, these different measurements of different criteria may lead to values that are largely different depending on the units. So you can have the economic benefit measured in euros, and then you can get billions. The number is order of magnitude of billions, while the perturbation of the river flow, according to some indicators, may be in the range 0.1. Okay, so how can we compare numbers that are so different? We need to rescale the criteria, the evaluation of the criteria. We need to rescale them in the same range. And typically what we do is to rescale each criteria in the range 0.1, where 0 means null, performance 0, 1 means max of the performance. This is one thing. Second thing that I want to point out about the weights, I forgot to say this before. By definition, weights usually sum up to 1. So here we have 4 weights. We assume that W1 plus W2 plus W3 plus W4 is equal to unity 1. Okay. Now, we have the 2 key questions. How can we make the rescaling? First question, it's quite easy. Second question, how to estimate the weights. This is a bit more complicated. So let's start with the simplest one, how to make the rescaling. Okay, I think you already had experiences in that. The criteria that is suggested by this method is to rescale the criteria, each criteria, through utility functions. Utility functions, they transform the criteria in the range 0, 1, and they are defined according to the bullet points that you see on the screen. Let me now unpin the camera. And let me change it. Good. And they are on the screen also, that is shared here. So utility function assign a real number in range 0, 1 to the performance of each alternative in such a way that an alternative is assigned a utility in such a way that to an alternative A, for instance, is assigned a utility greater than alternative B if and only if the individual prefers alternative A to alternative B. Okay, this is quite simple. So rescaled in the range 0, 1, and as I said, 0 means zero preference, 1 means max preference or max performance. So increasing utility means increasing performances, increasing preference. Okay. Now, by definition, how do we assign utilities? We need to satisfy three criteria. Utility 0 is assigned to the minimum of each criteria. As I said, utility 0 means no preference. So, of course, when we define a criteria, economic benefit, we also have a way to identify the minimum, because we estimate the economic benefit given by the dam. Then we estimate the economic benefit given by the reduce of losses, and the economic benefit given by precise irrigation. Okay. So once that we have estimated these three, we can see what is the minimum. So we give to the minimum 0, and we give 1 to the maximum. Okay. Now, the progress of utility from 0 to 1, you see on the figure that it's on the screen, can be linear. This is the simplest way to make the scaling. Can be linear. Okay. However, it can be also nonlinear. The only thing is that you have to respect the third criteria, bullet point here, the third constraint. Increasing utility is assigned to criteria values corresponding to increasing convenience. So the function must be increasing, monotonically increasing. It can't be decreasing. So as the economic benefit increases, the utility has to increase. Okay. Good. Or at least it doesn't have to decrease. Okay. But the progress between 0 and 1 can be arbitrary. No problem at all if it is a nonlinear function or whatever. In most of the application, it's indeed nonlinear. Okay. Good. Usually these utility functions are discussed with the stakeholders. And as I said, the linear increase, it's the most, let's say it's the easiest solution. But actually, you have to discuss with stakeholders. And there are methods to discuss utility function with stakeholders, which are similar to the method that we will see for establishing the weights. We don't go into the details. Let's assume for our purpose that the utility is assigned. Okay. the utility function. So we have the 4 criteria that are expressed in the range 0, 1, where 0 means the minimum, 1 means the maximum, and with, let's say, a linear increase between min and max. So we solved the first issue, utility function, and then the weights. Good. So how to estimate the weights? The suggestion given in this method is to split this quite complex decision into a sequence of pairwise comparisons, which means that I have here, I have 4 criteria. If you discuss with an audience what is the weight that we should give to each of them, it is a very complicated discussion. You can't manage it. It's much easier if you compare them 2 by 2, a pairwise comparison. So let me go back to our sketch. It's much better if you ask the audience, okay, let's discuss what is the weight, the importance of the net benefit with respect to the environmental impact. And then let's discuss what is the importance of the net benefit with respect to the river flow regime. And then let's discuss what is the importance of the net benefit with respect to the CO2 emissions. And then I have to discuss what is the importance of the environmental impact with respect to the river flow regime and the environmental impact with respect to CO2 emissions. Finally, I have to discuss what is the impact on river flow what is the importance of river flow regime with respect to the CO2 emissions. So we split the assessment. Instead of comparing 4 criteria all in once, we compare them 2 by 2. And the number of comparison is 1, 2, 3, 4, 5, 6. It is much easier, okay? And then we have to suggest a way to express the preference in this pairwise comparison. And the way is according to this table, okay? If they are equally important, okay, let's say that we give to the intensity of importance of net benefit with respect to the environmental impact, we give an importance of 1, which means that I consider that they are equivalent. Net benefit with respect to the environmental impact. If I give an importance of 9, it means that I consider the net benefit extremely more important than the environmental impact. Okay? And you make this comparison. And then you have to put everything together. First, you know, when you discuss with the stakeholders, even 2 by 2, of course, let's suppose that you compare the net benefit to an environmental impact, you will find some stakeholders saying, I give an importance of 9, which means net benefit is the first in this comparison, which means it is extremely more important than the second. You will have some stakeholders that will say 1 over 9, 1/9, which means that the score of 9 is given to the environmental impact with respect to the net benefit. So you can use intermediate scales. Okay, you can use 1.5, you can use 2, and if you want to say that the first term is less important than the second one, you have to go lower than 1. Okay, according to this scale, if the second term of comparison is more important, you can go up to 1/9. Okay. And then you have these 6 scores. And first of all, you have to reach an agreement with the audience for each of these comparisons. So if you have people who say 9, other people say 1/9, how to reach a compromise? This is a bit delicate, and you need, I mean, quite strong skills in communication to manage these discussions, because you have to emphasize what are the pros and cons of giving more weight to the environment, to the net benefit. Net benefit, as I said, is not only making money for one person, maybe making money for the state, and therefore it's everyone's money. So you understand that it is important how to vehiculate the information, and reaching a compromise doesn't mean that you take the average, because I mean, if you take the average of everything, at the end of the story, you don't do anything. Because, I mean, if you take the average of everything, you can't decide. It is difficult to reach a strong agreement. And for this reason, I said it would be more important, it would be advisable that we make this comparison, this assignment of weights before introducing the alternatives, if this is possible. Because, of course, if people already know that the alternatives are dumb with respect to precise irrigation, there are people that really don't want precise irrigation because they don't believe in it. They can't believe that with precise irrigation you solve the problem. And instead, when they look at a dam, they say, this is big, it's very huge. So for the same reason, some people don't believe in small reservoirs. They really don't trust them. They say it's too reduced. I really want a lot of water. Like you see a dam and you say, oh, I'm okay. And whatever happens with so much water, it's fine. So, I mean, this is a discussion that must be managed with the skills. And it's not easy, even if you compare them 2 by 2, okay? Okay, and then there is the question how we can put together the several evaluations, because let's suppose that you reach the agreement. I said that we have 6 evaluations to make 2 by 2. I go back to the sketch 1 second. 6 evaluation, net benefit with respect to the environmental impact, net benefit with respect to the impact on the flow regime, etc., 6 of them, okay? And let's suppose that we reached an agreement with scores and that the audience say, oh, yeah, we are happy with this. Okay, first of all, we need to visualize the scores, and given that they are 6 comparison with different scores, the best thing is to write a matrix. Okay, to write a matrix where I put 1 second, I change the camera, where I put each criteria in the rows and the columns, okay? So, let's write a matrix where I put here N, E, R, C, and here N, E, R, C, okay? So when you manage your discussion with the audience, you say, okay, let's compare them 2 by 2, and let's put the result into this matrix. Okay, let's compare net benefit with net benefit. Trivial, it's 1. Okay, same importance, same criteria, same importance. Okay. And then you ask the audience, okay, given that it's trivial, let's put in the diagonal 1, 1. Okay. Good. Now, let's discuss net benefit with respect to the environmental impact. You agree that it's more important, but not much more important. So let's put 3 here, okay? 3, look at the scale on the screen, means moderate importance, okay? Now, what if I go in this position? Environmental impact with the net benefit is the reciprocal of this comparison. So let's put 1/3 here. Is it clear? It's the reciprocal. Okay, good. Now, let's compare the net benefit with the river flow regime. Let's suppose that it's it's a bit more important, and or let's say it's much more important, 5, okay? 5 and then 1/5. And now, net benefit with respect to the CO2 emission. Let's suppose that you have people that say, no, really, I'm concerned about the CO2 emission, so I'm really willing to, okay, 1/9, okay? So 9. Good. So far, so good. Now it becomes a bit complicated because the next cell that I have to fill is environmental impact with respect to the river flow regime. And I can't really be free in expressing the preference because I have to take into account what is the result of what I evaluated here. So let's go back 1 second. Net benefit with respect to the environmental impact is moderate importance. Net benefit with respect to the river flow regime, strong importance. This means that I'm giving less weight to the river flow regime with respect to the net benefit, isn't it? So when I compare the environmental impact with the river flow regime, I can't say that this is a bit complicated. I have to think of what I'm saying. So if this is less important, okay, R is less important than E. So here I can't put something lower than 1. I have to put something like, I don't know, but 2, okay? And correct me if I am wrong. You understand that when you manage the discussion with the audience, this becomes the first row is okay. Everyone can say whatever they want, but when you come here, now, if I say that the CO2 emission is really more important than everything, now when I compare environmental impact with the CO2 emissions, once again, the environmental impact must have a lower weight with respect to the CO2 emission, like 1/9, okay? I forgot to put here 1/2. And now let me see here, 9. And you can see that there is a little bit of complication here. It's not easy to be coherent. Do you understand? The coherence of this matrix is not easy. Think of a situation where you have 16 indicators, a matrix that is 16 by 16. Becomes a bit heavy, okay? But, you know, of course, it's a complicated decision. Now, R with respect to C. So let me see here. For sure, C is important, more important. But here, if I put 1/9 again, there is something that you see, 999, same score. It is not really coherent because CO2 can't have the same score with respect to the 3 of them when I know that net benefit should be more important than E and much more important than R. So this means that probably here I shouldn't put 9. I should put something like 7. 7. And here I should put 1/7. And here 9, not really. I should put here 8. And here 1/8. Is it coherent? Well, maybe I think I was correct in adjusting a little bit in this way, but you understand that people who developed this method needed to introduce a quantitative assessment of coherence because we can't go just because the problem is that basing on the matrix, we will see it is very easy to estimate the weights. So the matrix puts together the decision, and it is very easy to estimate the weights. But if the matrix is not coherent, the weights are badly estimated. So fine, now we see how to estimate the weights based on this matrix. It's a simple calculus based on finding, let's say, how to say, calculus matriciale in English is calculus based on matrices. I don't have the translation, okay? But it is very simple, but the matrix should be coherent. Okay, so we need to discuss how to find the weights from this matrix first, and then coherence. Before I move forward, an obvious question by you is what should we learn of this? What I did so far, it's very simple. So my suggestion, of course, you don't have to learn by memory the example, but a typical question may be like at the oral, for instance, maybe analytical hierarchy process. So you should be able to explain in 5 minutes what is the rationale of this method. And so far, what I described is nothing very complicated. So I don't think that it is a problem to get ready to illustrate, okay, the concept. What we are discussing now, it's a bit more complicated, as you will see. So I will make clear what you may remember, prepare for the exam, and what's not. Okay, now how to estimate the weights from this matrix? Any questions so far? So this is an example of a matrix. It's not the same as the matrix that I put on the blackboard. So let's stick on the matrix that you see on the screen, because otherwise it becomes a problem to move forward. And what I did on the blackboard is different. But it doesn't matter, of course, depending on the audience, depending on the problem. What is important is that we try to make it coherent. What you see on the screen now, it's indeed close to coherence. It's not very coherent, but close to coherence. Okay. Let me change the camera. Now, weights. Now I'm mentioning something that I think it doesn't look very nice to you. And so what are the weights? I go back to the matrix. The weights are given by the right eigenvector of this matrix. Okay, eigenvector, eigenvalues. For sure, you studied these features of matrices. I'm not sure you remember them, but it is very easy. So first of all, I said right eigenvector. Usually, a matrix can have a left or a right eigenvector, but when we say simply eigenvector is the right one. So I use the formally correct terminology, principal right eigenvector, but if you prefer, you can just say eigenvector. Usually, as I said, when we say eigenvector of a matrix is the right one. So to make it simple, we need to find the eigenvector of this matrix. What is an eigenvector? And Wikipedia, 1 second, Wikipedia, or let's say here, because here I think there is the link eigenvector. Okay. Wikipedia, let's go down. 1 second. Overview of linear transformation. Linear transformation, I don't like it, but let me go to the calculus of matrices. Matrix theory. Okay, perfect. Anyway, you see the matrix, let's, okay, it's here. N by N matrix A. Okay, the matrix is A, okay? And the eigenvector is V. The matrix, if it is multiplied by a vector, which gives, as a result, the same vector multiplied by a scalar lambda, then this is the V is the eigenvector. So the eigenvector V is such that A multiplied by V, matrix A multiplied by vector V, gives, as a result, a scalar lambda that multiplies the same eigenvector V, okay? And the eigenvector is a n by 1 matrix, is a vector. Lambda is a scalar, which is called the eigenvalue, okay? So next question, how can I compute eigenvalue, eigenvector? In R is very simple. You give the matrix, and then there is a function. And if you want to see the function in R, you go to the exercise, suggested R code, and it is very simple, okay? And so I don't talk at the exam about eigenvalue, eigenvectors, but you understand that what is the utility of these concepts when you come to the practice. When you discuss with the audience, you don't have to discuss about eigenvalue and eigenvectors. You have to be very careful, because when you get entertained into communication, you have to use a language that the audience understands. And it is more or less the same as teaching, but in teaching, it's a bit different, because you are a student at the fourth year of your university career, 4 or 5, some of you 4, maybe some of you 5. So, I mean, you are supposed to know what is an eigenvalue and an eigenvector. And of course, I refresh, because, you know, this is something that you studied a long time ago. Your audience doesn't know at all what are eigenvalues and eigenvector. So if you get entertained into a discussion and you use a language that the audience doesn't understand, the audience will likely conclude that you are using an obscure language because you want to cheat them. So you have to avoid this feeling. And this is a problem also in the political system. When politics now is based on international economy more and more. And the international economy is not easy. So politicians, sometimes they talk by using terms that people cannot understand, because they talk about the BCE, they talk about the rates of the BCE, what is the effect of increasing rate, decreasing rates. So you understand that if they talk in these terms, then people may conclude that politicians are just trying to cheat. And given that you are a person that is prepared, that is accultured, that has studied, you are subjected to this accusation. And especially during this period where populism is very strong, it's prevailing. And you are a prepared person, you have studied, and you are in a way connected with the power. And therefore, because maybe that you were given a task by an authority, and you are subjected to the accusation of being, you know, in a way connected and having obscure goals. So you have to use a language that is appropriate to the audience. You have to be fully transparent. This is why transparency is becoming more and more important today. So you don't have to speak about eigenvalues and eigenvectors. You can just saying, okay, this is our evaluation, our assessment, and then from this matrix, we get these weights. You can jump to the conclusions, because if you look at the matrix, the conclusions, you can get a perception of what the conclusions are. If you look at the matrix on the blackboard, you get a perception that net benefit will have a weight that is not negligible, and the CO2 emissions should have a weight that is not negligible, okay? If we look at the matrix that was on the blackboard, on the screen here, instead, you see that here, the net benefit, it's given indeed with respect to environmental impact, river flow regime, and also with respect to CO2 emissions, it's given a significant importance. So I am expecting from this matrix that net benefit has quite a significant weights, and the environmental impact has a low weight. If you look just at the first row, you see, and the river flow regime should have a weight that is larger than the weight of the environmental impact, and the CO2 emission should have a weight that is in between R and E. So you may use also these kind of expectations that are understandable from the audience to provide an expectation of the result, so that they, when they see the results, even if they don't understand the computation, they in a way perceive that the results are reasonable. Okay. So if I compute the eigenvector should be rescaled to 1 to give the weights. Okay, so in this case, the eigenvector will be a n by 1 vector, which means a vector with 4 elements. The 4 elements are the 4 weights, but their sum is not equal to 1. So you have to rescale them linearly so that they have a sum that is equal to 1. And the first element of the vector will be the weight of n, net benefit. The second element, the weight of E. The third element, the weight of R. And the fourth element, the weight of C. Okay, let's see. I'm not sure if the results are given here. I wouldn't say that. Yeah, they are not given here. Anyway, because my expectation was to make an exercise, the exercise that you see linked, that would give a practical explanation. So the weight are not given here. Okay, let's see. Maybe that we have time also to go quickly through the exercise. But now let me talk about consistency, because as I said, the matrix, even if it's not consistent, will give you weights. But the weights, if the matrix is not consistent, are not reliable. So how to measure consistency? There is a simple method which is based on the statement that, look here, sorry, in the ideal case, fourth bullet points, in the ideal case of a fully consistent matrix, the eigenvalue lambda, a maximum eigenvalue, if you can drop maximum, because when you say eigenvalue, it is implicit that it's the maximum. The eigenvalue lambda is equal to the dimension of the matrix itself. So, which is in the above case 4, this 3 here is a mistake. Okay, so lambda should be equal to the dimension of the matrix 4. Okay, if the matrix is not fully consistent, the eigenvalue is not equivalent to the dimension of the matrix. So when you compute the eigenvector, you also compute the eigenvalue. If the eigenvalue is 4, the matrix is fully consistent. Now, if it is not equivalent to 4, we can compute a consistency matrix, index. We take the lambda minus n, okay, and which means that this difference, if lambda is equivalent to m, is 0, okay, and we divide it by n minus 1. This consistency index, which is 0 if the matrix is fully consistent, for increasing values, highlights lack of consistency. Now, the problem is that what if the matrix, the consistency index is not 0, but it is like 0.01? Is it acceptable, the approximation, or not? Because you understand that getting a matrix that is fully consistent, it may require an iterative procedure, which may not be needed actually, because when it becomes close to 0, and especially the iteration in this case may be simple, but if you have 10 criteria, you know, the iteration becomes really complicated. So what is a max acceptable value for CI, consistency index. Oh, there is an idea, a brilliant idea, which is the following one. Let me generate a random matrix with the only condition that I keep ones in the diagonal and I put reciprocals in the opposite position on the other part of the diagonal. But other than that, I generate a matrix that is fully random. In R, you can do this very simply. I mean, as I said, the only condition is that you put one in the diagonals and reciprocal in the opposite positions with respect to the diagonal. And of course, if you generate a random matrix, this is not consistent. And if you do this generation several times, you can obtain an indication of a value for CI that is acceptable. And this indication is obtained by computing the ratio between CI and RI. RI is sorry, once again. You compute the ratio between CI, the consistency of your matrix, and the value that you get from a fully random matrix repeated many times because you need several simulations. So you take the average. So basically, you divide this CI by RI. RI is the consistency index for a random matrix. R stays for random. And then you obtain this ratio. And then we have tables given by the method here for limiting values for Ri. So if the matrix is 1 by 1 or 2 by 2, it means that you need full consistency, clearly, because there is no way to be not consistent with a matrix that has only one pairwise comparison. There is no way. It's consistent for sure. If you have three criteria, this is the limiting value for Ri, and so you don't have to make your simulation. These are the values that have been made by simulations for you, values for Ri. And then the criteria says, if the ratio between the consistency index of your matrix, this one, and Ri is less than 0.1, so you have a 10% of allowance, then you are fine, okay? If it is, the ratio is larger than 0.1, you have to refine the matrix. So, once again, I compute the consistency index for the matrix, Ci. I compute the consistency index for a random matrix. Actually, I don't have to compute it because it's already given in this table. Because for every problem, I mean, the consistency index of the matrix, the reference value is the same. Okay, it depends only on the dimension of the matrix. And then I compute a ratio, which is called CR. CR, it is equal to CI divided by not R1, Ri, divided by Ri. And CR less than 0.1 is okay. Is okay. Let me see if everything is on the screen. Not, so let me change the camera, and now it is on the screen. Okay. That's it. Let me just check on the web page if I have. No, it's not here. Not here. 1 second. Okay. Okay, good. Okay, now let's have a look at the exercise because I think it may be worth dedicating 10 minutes to it because we have already the R code, so it is quite simple. Let me just see. Let me just application of pairwise comparison for decision making. Okay, it is here. And the exercise, let's read it, but it is related to the design of a small hydropower plant. And the hydropower plant can be designed, so the solution is only one, but what is variable, the different alternatives are the design flow for the hydropower plant, which means that for increasing design flow, I get more water from the river, okay? And the criteria which I want to use are the economic benefit, the impact on the fish community, because the impact on the fish community, because I take water from the river and therefore I have an impact on the fauna, and the impact on the landscape, and finally the fruition of the downstream river reach for recreational purposes. So I have 4 criteria. I need 4 utility functions because each of these criteria needs to be computed and rescaled. And the 4 utility functions are these ones. They are non-linear because if you put them on the screen, and it is quite easy, we will see with R, they are non-linear. They are piecewise linear functions, okay? Perfect, and then that's it. Let's get the R code, which is here. Okay, and let me open an R window. I don't have RStudio, as you know, here. Okay, let me modify the interface and let's put a font of 20. Good. I clear the screen. Okay, so I have the code here and the console behind. First of all, the code defines the utility functions by taking the data that I have put on the screen before, and the 4 utility functions are given into R, and then I can get them, okay? And then they are put into a matrix of utility functions. And let me see, copy. Let's put them here. Now I could make a plot of one of them. Let me see. U18, it is a bit 80, 90. In order to make a plot, I should make a vector of 8. Okay, let me create a vector of design flow. Why it doesn't come out here? Just 1 second. Okay, design flow equals C 80, 90, 100, 110, 120. And then the plot should be plot design flow, and let me see, U, okay, C, or C, U190, U1 100, U1 110. Okay, 80, I forgot. U180. Is U190. Okay, and U1 120. if I didn't make any mistake, we should get a plot. Okay, this is the utility function. And let me, 1 second, let me use a line, type equal to line. Okay, this is the utility function. It's linear, actually. This one is linear, okay? Anyway, these are the utility functions, and let's now look at the code. So this is the matrix of which I have to compute consistency. I called it prova, okay? The diagonals are 1, and these are the user likes, the preferences for the matrix, and these are the reciprocal, okay? And I put it into R, and then I will put it over the screen. Okay, prova equal array 0 dim equal P44. Now shift this. Okay, this is the matrix. 1 second, I clear the screen. This is the matrix. You see that it has 1 over the diagonal and reciprocal in the opposite position with respect to the diagonals. So what I see here is that I think the criteria number 3 has a larger weight than the criteria number 1 and 2. And criteria 4 has a lower weight with respect to criteria 1 and 2. So I expect that the more important criteria is 3. So the weight of 3, I am expecting a larger weight. Now, let's look here. This is the computation of the eigenvectors into R. And I don't make any comment on this. The only thing is I want to visualize the resulting weights. And you see that the weights are rescaled. If you see the last instruction that I selected, it is divided by the sum of the weights. Okay, let me put it here. And let's see the weights. Okay, so what so let me see, my expectation was, yeah, okay. I was wrong. The third is the least important, and the fourth is the more important. Yes, this is matching my expectation. And these are the weights: consistency, C1, computation very simple, and then CR. It's 0.0116. It's consistent, yes. It's less than 0.1. Okay, the important thing here is, I clear the screen, is the matrix and the weights, which indeed match our expectation. Because if I say that criteria 1 is more important than criteria 3 and less important than criteria 4, it's clear that criteria 4 must have the largest weight, and criteria 3 should have the lower weight. That's it. Questions before we go for the coffee and the lab? So let me see. Okay. Okay, now the plan is, first of all, let me close the lecturing, okay, and with the recording. So you are still in time to ask any question you may have. Let me close this. And this, okay, perfect. I forgot one thing. Let me just to have a look again at the links. So for preparing your exam, these are the links you should concentrate on. Introduction, okay? And be careful of the introduction. There are some numbers which may be asked, okay? Like what is the order of magnitude of climate change, global warming, CO2 emissions? Okay, so introduction is definitely to study. The second link, the learning process adopted in the course, it's not to be prepared for the exam, okay? Nothing, okay? Earth system, so prepare the first, don't prepare the second link. Earth system, yes, a typical question, what are the spheres, what is the definition of spheres of the Earth system, and have a look at this. You don't have to learn numbers here, so you don't have to look at this figure and learn these numbers, okay? But to get an understanding of what is how their system works. Nonlinearity, yes, learn these two conditions. This may happen in the quiz that you get a question on nonlinearity. Tipping points, typical question, what is a tipping point also for the quiz? And you have 4 alternatives and 3 are plain wrong, okay? So have a look at this. And what is a deterministic model? What is a stochastic model? Yes, may happen, okay? What is a state variable? It may happen into a model. And this conservation equations, I consider this question quite a not easy question. So I may ask this question if I want to make sure that you deserve the highest mark. Okay. Reynolds transport theorem. I mean, it is a typical question in order to check if you get the highest mark. One thing, last year, at the first exam, I gave the student the opportunity to skip the oral if they turned out to be very good in the quiz. I'm not sure I will give this opportunity this year. Don't take it for granted, because it depends on how many you are and how you perform in the quiz, what kind of questions you got into the quiz, which is random. So it may be that the same person, they got the same mark in the quiz. To one person, I give the opportunity, and to the other person not. Why? Because the random composition of the quiz made the quiz for one person easier than the other person. I am aware of these limitations of the random quizzes, and therefore I try to compensate in some cases. In some cases, I may see that the student was unlucky because it got several difficult questions into the quiz, but the student was very good. And therefore I may offer to get the max mark even without taking the oral. But this depends really on the situation. Don't take it for granted, okay? I'm mentioning this because last year there were some discussions in students that said, you allowed him to take the mark without the oral, and why I'm not allowed to? Because you got a different quiz. This is the reply, okay? And otherwise, I realize that if I treat all the quizzes in the same way, there are some distortions, and I want absolutely to avoid distortions due to randomness. Okay. I would say that I don't have anything more to say about this. And then climate change problem. Remember the orders of magnitude of the climate change, okay? So what is the urban heat island profile? What is the urban heat island? Yes, it may happen. And order of magnitude of global warming again. And what is solar irradiance? Yes, may happen. Okay. And what is the albedo? May happen. We are talking about climate change. We have to know what is the albedo, and order of magnitude of global precipitation, order of magnitude of CO2 emissions, okay? And you will have to choose between different answers, and I mean, they are not similar. There is only one question right, and the other are plain wrong. By the way, on Virtuale, you should have the opportunity to make a self-assessment test, and it's already available, and you can take it whenever times how many times as you like. And it is anonymous. It doesn't give you the correct answers. It gives to you only the percentage of the right questions. And this is something that I can't avoid. If I want to make it anonymous, I can't give the answers to the self-assessment test. I can only give a performance measure. If you have any question, let me know. And what are emission scenarios? Yes, may happen. And what is a feedback? May happen. And I think that's it. And then there is sustainability in the 21st century. As I said, this is not something that you need to prepare for the exam, okay? Risk-based adaptation design is probably the most important lecture of the risk. The risk equation is asked several times, okay? So pay attention to this. What is vulnerability? What is exposure? You will get several questions in the quiz, several variants of the same question, which aims to check if you really can get the concept of risk, exposure, vulnerability. Climate change and water, you don't have to prepare it for the exam. Okay, sustainable management of water resources, yes. The linear reservoir is a typical question, and including the proof, I'm checking if it is here. I think so. No, it's not here, the linear reservoir. So I'm sorry, I need to correct myself. This one is, let me see. I think what you need to get here, you may get questions on the Köppen climate classification. You may get questions of the order of magnitude of fresh water. What is the percentage of fresh water with respect to the total? 3%, okay? And you may get a question, what is the percentage of fresh water with respect to the total? About 3%, about 30%, about 100%. This is the kind of questions that you may expect. So you don't need to know the precise number, 2.5 rather than 3, okay, in order to identify the correct answer. So, yeah, this one. Inductive and deductive estimation. I thought. Here, what you need to learn, linear regression, yes, this is a typical question, and also the linear reservoir, I think it is here. And Rand's theory, yeah, you may get questions, but it is very narrative, you know, so there are you don't have to learn a relationship. Long-term persistence, forget about it for the exam. And here it's rain-for-runoff modeling, yeah. Linear reservoir, rational formula, typical question for the exam because it's very simple. So, but try to look also try to read not only the formula, but also the introduction, the assumptions, okay, and the linear reservoir. And I may ask you also if you can, the oral, if I want to make sure that you deserve the highest mark, I could ask you to demonstrate, to develop the equations, okay? And this picture here, you may find also in the quiz a question on recognize the right diagram of output from the linear reservoir with constant rainfall, and you get 3 diagrams and you have to choose. So this one is important. Okay, and model calibration and validation, the objective functions, yeah, you get questions on that. And decision theory, I mean, there is a narrative part, and what I explained today, I think I already gave to you the details, that's fine. And what is a bottom-up and top-down approach? Info gap, if you could define what is an opportuneness function, what is a robustness function, this is important, okay? And you don't really need to learn these definitions. Sorry for this visualization problem. As I mentioned to you, here and only here, I get these in Chrome. And you don't need to learn these equations, okay? But what is a robustness function, opportuneness function? Yes. Okay. Good. Now, I think I can share the screen and I can stop the registration. And I wanted to thank you